Hi everyone, just joined. We're waiting a few more minutes, a couple more minutes, and then we'll start. I will have a short presentation to set the stage, and then we'll go for the agenda. One more minute, and we'll start. I'll start sharing my screen. Um, Can you guys see it? And can anyone confirm?
Yep, yep.
All right. Yeah, I mean, we're 2 minutes over. This meeting is then in any case recorded. So I will just start. And again, I will have just a short presentation to set the stage. Welcome everyone to the breakout room number 2. Thanks a lot for attending. I spent this couple of weeks to just do a recap of the situation. And I will post this online later on, but this is a kind of table that compares the NIST post-quantum signature schemes and different axes. Um, so basically, last week we have seen a bit of lattice signature schemes, and here is a quick recap of what we've seen so far. For example, like the signal size Falcon is shorter than the lithium, so it's in green. And the gas precompiles we've seen Renault and Simon showing that for the precompiled the gas Falcon is as well cheaper. We know this already, and it's kind of important. For aggregating the signatures, it's really important for the mempool, but probably we're going to see this in the future. Falcon has some solution that is based on some paper they call Labrador, but with dilithium it's not so friendly. And where Falcon has issues at the moment is, and dilithium is better, is on the hardware. Historically, we know that Falcon relies for signing on floating point, and this is actually for Ledger or this kind of hardware. Is might be complicated. And yeah, we'll see in probably some future calls the threshold friendliness for post-quantum signatures. In any case, a disaster. We have today some presentation on the on Sphinx TSS, and yeah, this is basically it. Today we are a lot of topics are at least for the presentation about symmetric symmetric primitives that are based on hashing. So, and here we have as well some recap on the standard Sphinx. We see that, yeah, we see a bit of red here and there. And yeah, this is the agenda. We will have Michael presenting their version of the hash-based signature schemes that is more efficient for blockchains. Then actually we have Nico that will have a cool demo showing this in action, and we'll have Yasvandan and Naman seeing the difficulty of having threshold signatures for hash-based schemes. And then ideally we will have some more minutes, ideally 20, 30 minutes to discuss stuff. And if you don't have any more questions, I will give the stage to Michael. So we can start early. Michael, the stage is yours.
Thank you. You should be able to see my screen now.
Yep, all good.
All good. So, yeah, I will give a brief summary of what you can do with hash-based schemes for the scenarios such as blockchains. We specifically looked at Bitcoin application, but I think most of our findings are in general applicable to the blockchain environment. So obviously, while we're here, we have the quantum threat. We want to move to post-quantum solutions. So in case when or whatever quantum computer appears, we're safe, we're secure. And the options are actually um, quite, there are quite a lot of options. You can do lattices, you can do hash-based. For lattices, you have a variety of schemes. Unfortunately, none of them is as good as our classical counterparts. And today we will look at hash-based schemes and what they can offer, what are the upsides, what are the downsides. And the first and arguably the most important upside of the hash-based schemes is their security. So it's super conservative. Everybody is hashing everywhere. There is no problem with that. If we don't have hash functions, we essentially don't have almost any cryptography. All the lattice-based schemes still use hash functions. So this is as minimal as you can get. But the problem, as we saw on the slides before, is that the sizes are quite large. There is this scheme Sphinx Plus, which has been standardized, and for the best sizes, kind of there are multiple parameters was selected, and if we select the one with the best size, I think it's something like 7.5 kilobytes. That's huge. Where does this come from? Is we have this structure. It's called a hypertree. So essentially, it's a Merkle tree at the top. The leaves of the Merkle tree are one-time signature schemes, so they can only sign once, and we use those signatures to sign Merkle trees on the next level, and so on and so on and so on, until we get to the very bottom, where we use a so-called few times signature scheme, which we actually use to sign the message. So we have this kind of certification kind of. You have this root of the top Merkle tree, and then you show, okay, I do this signature and I attach the authentication pass for here. I do this signature authentication pass and so on, so on, so on. And so you have to include everything that we just discussed, and this where the sizes come from. But there are a couple of optimizations. The core idea here is that this tree can be used only for a limited number of signings. Essentially, if we forget about few times signatures, the idea is to create a tree big enough so that if I sample a leaf at random, they will not collide. With the few times signatures, they should not collide too often, but that's the small detail. And so NIST asked for a scheme that will be able to perform 2 to the 64 signing operations. And for our applications, we don't need 2 to the 64 signatures. That's a definite statement. We looked at some numbers, and I think even like 2 to the 35 signatures of size 3 kilobyte will fulfill the whole Bitcoin blocks for, I don't know, 100 years or something like this. I should double check the parameters. But yeah, the 2 to the 64 is a huge overkill. And this is not a novel idea, that actually you can limit the number of signatures for hash-based schemes. And there is, I believe, currently also an ongoing process in NIST to standardize a scheme with fewer number of signatures. So uh, on the slide, you can see the presentation by Stefan and Jade that were also searching for different parameters by just reducing the allowed number of signatures. As you can see, so these green triangles here, this is different parameters for 2 to the 64 signings. If we go as low as here, it is somewhere around 7,000, I think, here. But if we go, for example, for 2 to the 20 signatures, you can get much, much smaller signature sizes. So this is the first and arguably the most obvious modification that you can make is decide in your scenario what is the limit that you are happy with, and just limit that. The upside of doing nothing else is that essentially you more or less can reuse the existing implementations. Maybe in the future you will be able to use some hardware acceleration, but this hardware acceleration question mark if it will be there or not, specifically for Sphinx, and whether you could use that acceleration with different parameters. This is not entirely obviously, but at least you can reuse implementations. Then, if you think, okay, I'm still happy to deviate from the standard and arguably the most popular version of hash-based signatures, then there are also different modifications that you can implement. So, as you saw on the slides, we have different building blocks here. We have one-time signature schemes. We have few-time signature schemes here. And so if you change them, because researchers came up with arguably something better, you can also change the performance. And most of these modifications, what they do is they put extra effort on the signer. So the signer needs to do more work, but this will either reduce the sizes or verification complexity. Sometimes we increase both the citing complexity and verification complexity to get more, to reduce the signatures even more. And so what we can see this on this slide, we have Sphinx. This is the first line. And as I said, yes, 7,872 bytes. Yeah, this is pretty sad. And we can start limiting the number of signatures. And here in this column, we say, okay, which modifications to apply. And already here you can see that we can get as low as 4,600 with similar signing time and similar verification time. Yeah, okay, this is twice worse, but this is no big deal. And here this the same. And if we apply even more modifications, then we can get as low as 4 kilobytes for 2 to the 40. And 2 to the 40 is arguably also an overkill. Then if you're happy to go even lower, it's 2 to the 30, you can reach 3.5 kilobytes for different cases. Depends on how many modifications you want, and depends on how much are you happy to put on the verifier. And I must say here, yeah, you have the numbers 8,000 compared to 2,000 here. This is quite low actually. The 2,000 hashes to compute is not a big deal for the verifier. So it is arguably completely fine to push it even to the 10,000s. This is not a big problem here. And if you're happy with around 1 million signatures, you can go even below 3 kilobytes. And I think this is really nice because we start with almost 8 kilobytes signatures, and we actually can get to somewhere around 3 kilobytes, which is much better. And people always say, okay, lattice-based, they have quite small signatures compared to lattices, compared to hash-based. And again, yes, the signatures are smaller, but for most of the blockchain applications, you should actually compare signature plus the public key, because you will need to put both of them on chain. And if we compare Dilithium with our modified hash-based parameters, okay, yes, Dilithium can support more, but do we need more? And then the sizes can even go, in these scenarios, can even go better. And another, I think, which is quite popular topic right now, especially in Bitcoin, is a scheme which was called shrinks, which introduces the idea of mixing two different hash-based schemes together. The thing is, when we talk about Sphinx Plus, it is a stateless scheme. That means you do this signing, and you don't need to update your secret key, so that you just do the signatures and you don't need to modify your secret key. There are stateful hash-based signature schemes, and an example you can see on the left side. Essentially, you do a Merkle tree with one-time signatures at the bottom. For example, this one can sign 4 messages. Yeah, you need to remember which ones you have already used. So the first message you sign with the first leaf, the second message with the second one, third with the third, and fourth with the fourth. If you run out of leaves, you're done, and you shouldn't reuse the same leaf twice. And such schemes are more efficient than stateless. But the problem is, you have to store and modify the state. And this is especially annoying if you want to do backups and then restore the backup. The backup should have the state, and every time you sign, you kind of need to update the backup, otherwise you won't be able to use it. And so this is a little bit annoying. But moreover, what we can do is, instead of using a Merkle tree, kind of a usually balanced Merkle tree, we can use an unbalanced Merkle tree, which means that the first leaf is just one path away from the root. And so the first signature will be super cheap. I think, according to our computations, it's something like 300 bytes. 300 bytes is just nothing in the post-quantum cases. I don't think any other signature can achieve 300 bytes. Yeah, this is nothing. And the second one will grow. So here you will need to include more because you need to include the identification pass. So you will need extra nodes to include, and so on. But also, to mitigate the statefulness, we can combine our stateful scheme with the stateless version. Okay, here it's written Sphinx Plus, but essentially you can plug in whatever we discussed on the previous slides. And then you have this arguably nice combination of statefulness with very cheap signatures, plus the stateless for a backup in case something went wrong. This has also its potential downsides, because stateful is still annoying to work with. You still need to update the state. If you generate multiple addresses, so essentially you generate multiple key pairs, you need to store the state for each key pair. You cannot allow 2 signing devices to operate in parallel. There are a lot of caveats there as well, but as a plus, you get quite small signatures. I think this kind of summarizes overall the ideas that we discovered so far. I think I can also we also checked different extra applications as threshold signatures or multi-signatures that will be later discussed during this call. But from our findings so far, there was some approaches, but none of them are super efficient and don't give too much. Maybe there is something extra that we don't know, but let's see that later in this call.
Mike, thanks a lot for your presentation. Was really interesting result to see that actually happening. And I will ask you if to please, if you can answer. There are some questions on the chat. Interest of time, if you can answer in the chat rather than by voice. So
Sure.
We'll give the stage to Nico. And actually, it's really beautiful because Nico, as far as I know, already implemented part of your work, and will show it in action on Ethereum. So I cannot imagine any better segue. Nico, if you're here, this is your time to shine.
Thank you. So I'm going to try to share my screen. Let's see. Okay. Can you see my screen now?
Yeah, we see it. All good.
I have a short presentation. So I figured out that like it's better to give a short presentation rather than just, showing you
For sure.
wait, hold on, slideshow. Okay. All right. So yeah, I just wanted to make a quick presentation rather than showing you my script and my deployment because would be just me typing a few commands in the terminal. So what did I do? I actually tweaked the Blockstream research work. So Blockstream has a very nice repo where you can look for Sphinx parameters that are nice for you. So in the EVM context, you have slightly different constraints because you have gas, and basically it becomes a research of the most efficient parameters within the EVM constraints. So same as for other blockchain, you have the reuse constraints. So you want to be able to reuse your scheme a certain number of time so that people don't have to change wallets all the time. And to combine this with some gas efficiency. So doing this, I ended up finding a bunch of sweet spots, and I tried two of them in deployment. So these are the sweet spot that I found, and good to mention here that I looked a little bit, but I didn't look that much. So maybe someone can find a better sweet spot, and there is a lot of design space here. So yeah, this is just a presentation to open the discussion around this, but it is by no means the canonical or the best solution that I found.
Because just trying to
So
decipher this, is this like if you try to correlate this with the presentation of Mike, is this like the strings or are the XMSS or the Sphinx? Which family is this? Because it's a
yeah,
bit
so
sorry.
so these are different variants of that are actually explained in the let me check this link. Oh. The variants are actually explained in the repo here. So W plus C is Sphinx plus with VOTs with counter-based VOTs, so no checks from on chain. So you can find everything, like all the details, all the different families inside the repo, inside the Sphinx parameters repo. So it's basically just a bunch of variants of Sphinx, and they have different properties. So if I go back to slideshow, yeah. So these are different families of Sphinx, and I selected these ones because they just look nice, not too big, somewhat easy to verify. And yeah, so I have this small repo where I try to do it. And earlier today, I deployed them on a test network just to find the real cost. So I ended up with transactions that are about 400K, but these are 4337 transactions. So there is a large overhead for the 4337 framework. So there is the overhead for the entry point and a bunch of different things. So these are hybrid accounts that are relying both on a K1 signature and the post-quantum signature. So I copied the work from Zikanox, who presented last time, and I simply tweaked it with my two schemes. And it's quite interesting because we can have under 200K gas signature with the C2 scheme and 250K gas with the C3 scheme. So this is something that is big. It's about 10 times bigger than a regular K1 signature, but it's not crazy big. So this is something doable. And yes, so you have the cost breakdown here. So you can see the debug trace from the transactions. I will publish the transaction probably with the repo so everyone can look at them. And yes, so this scheme retains, so it's to make a parallel with the previous presentation. This one is okay with at 120 bits with 2 to the 20 signature. So that's roughly 1 million signature at 128 bits of security. Then it goes down quite nicely because it still allows you for like 4 million signatures up to 112 bits of security. So if we bring that back to the context of a wallet, you don't have that many people who sign millions of transactions on chain. And if you do sign millions of transactions, you probably are a very, very advanced user, so you somewhat know what you do. C3 is slightly more expensive, but retains more security. So you can keep about 140 million transaction at 120 bits of security. So that's really a lot. Actually, I checked quickly, and nobody has hundreds of millions of transactions with the same wallet pair on the execution layer. So yeah, it is a very interesting design space to explore. So I have this meme right now. The best competitor that we have is this guy. And yeah, to finish the presentation, I did all of this very quickly. I'm not a cryptographer. I have a lot of cryptographers in my colleagues and friends, so we will be looking into it. And maybe I'm wrong. So if I'm wrong, we will just git it and find another set of parameters that is the good one. So yeah, that's it for today. I will paste the.
Call me impressed, just because like it's true that are 10 times bigger than ACDSA, but it's as well 10 times less than the Falcon we've seen last week. So it's actually it's remarkable low number of gas, right?
Yep.
The question I will have, probably I should have a question before as well to Mike, was about the creation of the. Yeah, my question was really about the key generation. I know that like for hash basis, the key generation is kind of it's hard, but yeah, I will ask him offline apparently.
Yeah, in my schemes, I did take a very conservative D parameter so that you don't have to generate a Merkle tree that would be too big. And I took a parameter that is okay-ish for hardware wallets so that eventually it could be generating the entire keygen in like a few seconds on existing hardware. But I didn't try that, so we'll see.
All right, so I'm take offline. So yeah, whoever is left, there is the next presentation. I see a lot of people joining back, so it's good. So everyone, yeah, for the next goal, we have to fix this. I don't know how, to be fair. There were like, it looks like there was a script of that joined and did this, whatever it is. I don't know. I didn't understand what it was saying. So yeah. So if the next presenter is here, I will invite them to join and share the screen.
So should I go ahead and join? I mean, share my screen?
Yeah, please.
Okay, let's go. Can you see my screen?
Yes, all good.
Okay. Okay, so maybe I can go ahead and start then. So, hi, I'm Yashwant. I go by Yash. I'll be speaking about the practical challenges for designing threshold signing protocols for hash-based signature schemes. So this covers a fairly broad class of signatures, including Sphinx and XMSS and so on. This is joint work with Naman Kumar and Anand Vanegas. And I'll sort of set up the scope for this presentation first, as in the context for the talk, and then Naman will get into the technical bits. All right, so when I say threshold distributed signing, what I'm referring to is basically specialized multi-party computation protocols or specialized MPC protocols that compute the signing algorithm of a signature in a decentralized way. And importantly, while keeping the signing key itself secret shared. Right? And this is a common paradigm in key management. So this gets rid of, this gives one way to mitigate this single point of failure problem in key management. Right? And it's commonly deployed in the classical setting. So I want to make clear that the scope of this talk is specifically for MPC protocols that compute signatures that verify with the original algorithm. Right? So I'm not looking at settings where the verifier has changed. So I'm not going to talk about, for example, aggregate signatures or multi-signatures that have like concatenations of the original signature. So the litmus test basically is if the verifier can't tell whether the signature has been produced by the threshold scheme or the single party original signing algorithm, then that sort of fits in the scope of this talk. And of course, we want some notion of corruption resilience. That is, even if some devices are compromised, then the signing key should stay safe. And because I'm going to be talking about barriers, I will make the adversary as restricted as possible. That is, I'm going to consider only passive security. That is, everyone follows the protocol and there are no deviations, right, in the threshold signing protocol. So we have classic results that tell us that any algorithm that you can write down efficiently, you can also decentralize using classic MPC techniques. But there are differences that come up in how efficient these things are in practice. In particular, the structure of the algorithm sort of determines how efficient the MPC protocol for it is going to be. And this is not a new concept for post-quantum. We already have some idea of how this plays out in the classical setting. So, for example, if you're familiar with threshold protocols for signing with BLS, they're basically trivial. Schnorr or FDSA have classic threshold signing protocols that go back decades. They're quite simple to analyze and design and implement. RSA is maybe not so popular these days in this context, but RSA also does support efficient threshold signing, but the key generation for RSA involves some very complex MPC. ECDSA kind of sits in between these. It's, I would say, non-trivial, but still practical because it is actually used, and the state of the art for ECDSA has evolved over time. Right. So just like a quick overview of the history of this threshold ECDSA has been studied since way back when ECDSA itself was actually standardized, and people started with sort of limited schemes, like for example, with a trusted dealer or an honest majority or something. And just as a point of reference, in 2017, there were these authors, Lee et al., that used generic tools to benchmark ECDSA signing, like in a threshold setting. And it was quite slow on the order of several tens of minutes and like half a terabyte of data transmitted or something. This is just to generate one signature. This useful as a data point. And at roughly the same time, or very soon after this, Little gave this custom protocol for threshold ECDSA signing that is substantially more efficient and very clearly deployable, like tens of milliseconds and a few kilobytes exchanged in threshold signing for ECDSA. And at this point, it became clear that there is a business use case for this and that it is a solvable problem. And so there's been this explosion of works in the last few years that do threshold ECDSA signing, and it's been deployed. And this is a, like a settled story. But when it comes to post-quantum schemes, arguably lattice and hash-based cryptography are among the most widely accepted. And dilithium, or MLTSA as it's known, has seen a good amount of progress in threshold signing. Right? So it started with the generic scheme a few years ago. Like Cosmo Smart estimated that it would cost like tens of milliseconds over hundreds of megabytes to sign to use generic MPC. And very recently, Shelley et al. Constructed this very efficient custom protocol that admittedly works in a bit of a restricted setting, but it's very clearly deployable, like on the order of tens of milliseconds, hundreds of KB. And the question that this begs is if we can hope for like a similar line of evolution with hash-based schemes. We know that we can use generic MPC to compute hash-based schemes in a threshold way? And can we hope that with enough research firepower that we can get custom protocols that perform as well or close to the same efficiency as the classical schemes, right? So what do we actually know about hash-based schemes in this context? So I'd like to divide these hash-based schemes into two broad categories. That one is NIST-based. If you come across terms like MPC in the head or just NIST submission faced or picnic or something, that's the class of schemes I'm referring to over there, where essentially the public key is a one-way function applied to the signing key. And a signature is essentially a proof of knowledge of the signing key with the message incorporated somehow, right? Like into the sort or challenge or something. And on the other hand, there's one-time signature-based schemes. So there's no good way to succinctly characterize this class of techniques, but essentially you can think of this as starting from Lamport and then building upwards, like this WOTS and then XMSS and Sphinx and so on. Where the basic building block is a one-time signature, and then it's composed in interesting ways. And unfortunately, neither of these categories of schemes, at least the standard schemes, are known to support efficient threshold signing out of the box. And in this regard, we do have some idea as to why for the NIST-based schemes. That is, there's this result that my co-authors and I published a couple of years ago at Crypto, which showed that there is this inherent barrier to going beyond the generic MPC class of techniques for NIST-based signatures, right? Which is at a very high level, the intuition is that there's always going to be some hash queries that need to be made in order to compute the signature correctly, but also the hash has to be computed on private inputs. So the natural conclusion from this is that there's essentially no general way to handle this problem other than using generic MPC, that you have to perform this hash evaluation on private inputs in a like non-black box way, like you use generic tools to compute these things. And in this work that Naman will be speaking about a bit after this is basically extending the analysis that we had for the NIST-based setting to the more general one-time signature-based setting. So we prove very similar results that inherently there's always going to be some private hash queries that you have to compute using a generic MPC. So what are the implications for this? I again want to highlight that when we're talking about standard or standardized signatures, typically the hash function involved is SHA, and MPC for SHA tends to be quite expensive because they have a large circuit representation. Concretely, for XMSS, the standard parameters, we think of this as at least several seconds per signature. You could think of ways to work around this. Like you have to do this work at some point, right? So maybe you can offload this work to a preprocessing phase. In fact, that's how it had to work for XMSS because you effectively pre-compute all the signatures. So online signing is efficient, like on the order of milliseconds or microseconds, but the several seconds per signature is pushed to some offline phase, but that involves like state management and so on. You could also think about changing the hash function to something that's more arithmetic friendly. We haven't explored this ourselves. I believe there's a new paper in the journal, in this new crypto journal that the CIC that explores, trade-offs with even arithmetic friendly hash functions. But then again, this would not be standard compliant. That there could be situations where it makes sense to consider these kinds of workarounds, but at least as our analysis shows, the current modes of operation that we're used to for threshold signing, it'd be quite expensive to sustain this while also being compatible with standard hash-based schemes such as XMSS, Sphinx, and so on. And yes, with that, I'll hand it over to Naman to give some more insight about the technical aspect of this.
Yeah, thanks, Yash. Am I audible? Can you hear me?
Oh, good.
Okay, let me just share my screen. There we go. Can you see my full screen?
We do actually, yes.
Yeah. Okay, yeah, thanks. Yeah, so as Yash said, I'm going to be continuing on this and presenting you some of the technical ideas behind this idea that we have. So just to recall, we're going to be in this work, like what we do is we study hash-based signature schemes just from a general theoretical perspective, and we're interested in understanding, just the technical feasibility of what it means to like thresholdize these hash-based signatures. And yeah, I'll give you some additional introduction, some additional background. Talk about some of the scope of how the scope of schemes that our work covers, and then show some possibility results related to what you can and what you can't do if you're planning on threshold signing hash-based signatures, and basically also some idea of what conclusions you should draw from it. So just review, so Yash presented these like previous two definitions of like hash-based schemes. The first are these, these schemes that are based on NISX, like MPC in the head and so on. And the other are these like, more general purpose hash-based schemes. So it's kind of important to like understand which schemes I'm talking about here to see the full scope of like this, the limitations that we identify. So in general, like the way we define hash-based schemes are basically schemes that are based off of this idea of Lamport one-time signatures, where secret key is just like two randomly sampled strings, and the verification key is the hashes of these two strings, and signing is as simple as revealing the preimage of a hash. So, of course, this authenticates because only the signer knows the preimage of this. Yeah, and in general, like as was previously presented, these like hash-based signatures, they follow the same ideas. You like extend these using these Merkle tree style constructions, and you basically build these like nearly all of the hash-based schemes that we're talking about, including the standardized ones, such as Sphinx, Sphinx Plus, or like XMSS and so on. Like all of them are, these all like follow this like similar paradigm of using some kind of like this like Lamport one-time signature scheme as like a base unit, and ultimately like at the final step of like this the verification procedure is always like checking the preimage of something. And yeah, I mean the advantage here is that they use only this like cryptographic hash function. So because we're looking at these schemes from like a theoretical perspective, what we are doing is we study we study this in the random oracle model, and in particular, we show that the security, our definition of hash-based schemes is that the security reduction requires no hardness outside the random oracle. So basically, security is based merely on like whatever is provided by the hash function itself. Okay, so now just to get a bit more into the technical details, the threshold signing, we have to actually talk about what we mean by threshold signing. So for example, in general, you can always just like threshold sign any signature by using generic MPC. So if you have the secret key verification key, you feed this into some, and you have like a bunch of parties, you can just perform some like generic MPC for this, for the signing algorithm and like obtain a signature. Of course, this can broadly be like very inefficient. The downside is, as Yash said, you have to like evaluate SHA inside of an MPC, and this is like, of course, very, very expensive because like, I mean, the circuit size of like SHA is like quite large. Especially if you have to do it many, many times, which in the schemes that we talk about, often like, you have to do it thousands, or in the case of like Sphinx Plus, even like millions and millions of SHA evaluations are required for a single signature. And in this setting, like generic MPC just like becomes like prohibitively hard. Yeah, and so what we do is we define this notion of like black box oracle calls, in which case, of course, like a very nice signing protocol, threshold signing protocol would be one in which like there are no, you never have to evaluate SHA inside MPC at all. Like, every single oracle call or like every single hash evaluation is done by one of the parties. This is like the alternative to this, and this is, and we call this oracle respecting distributed computation. So the key result is that we can like define this like extractability property, which of hash-based signatures. We borrow this from NISX, and then we like rule out like such kind of threshold signing, threshold signing protocols altogether. Which, as I previously said, these are oracle respecting ones, in which case like none of the hashes are like evaluated inside of an MPC. We can like broadly rule this out for all but one corruptions, and in our model, it's pretty general. So in this case, we consider no CRS, no dealer, and no pre-processing. And I'll talk a little bit more about what it means in terms of this later. So yeah, just to get a bit into the technical ideas, if you talk about like NISX in the random oracle model, then like the idea is like pretty simple. There is this like if we want to like verify knowledge, then there is this thing called an extractor, which like simply takes in the proof, and it takes in like the set of queries that are performed by like the prover, and then using this it can like extract a witness. So this is exactly how you end up proving proof of knowledge in the first place, because a witness for like your underlying NP problem that you're trying to prove can be reconstructed based on like what the prover does. And similarly, we can define extractability for signatures, in which case, there is some extractor, which if you're given like the Oracle queries that were made during signing, and you're given the message and so on, along with the signature that was generated, what you can do is you can like produce a new signature. So in the end, it reduces to the fact that like, these Oracle queries that were made during signing, if made public, then, it is possible to like forge a signature based on this. Okay, so we have this notion of like KT extractability. It's like, it's a pretty simple definition. You don't need to look at it for now. All this means is that, it's a way of formalizing that if the Oracle queries during signing are like made public, then this like causes problems. You're allowed to forge. This definition, of course, is only useful if it applies to like signature schemes that are actually in the real world. So this is in fact true. Like for XMSS, Sphinx and Sphinx Plus, this is all true. And the intuition really is that basically any kind of like natural scheme that you can come up with, natural hash-based signature scheme in which the security reduces only to the hash function, it uses some kind of like Lamport as its like base unit. And so if this is the case, right, then the way that as I presented previously about Lamport, the idea is that like the only real way in which you can get like authentication from Lamport signatures is by revealing the pre-image. And if a scheme does this, then it is like pretty easily like you can show it to be extractable. So like basically any natural hash-based scheme that you can come up with, like it has this property. Yeah. So of course, now we have these like hash-based signature schemes. What exactly are we saying about them? Well, the idea is that like if you have some kind of like protocol that like signs this in like this Oracle distributed in like this Oracle respecting manner, then you can like basically there's a way for the adversary to be able to like forge a signature on any message of its choice, which works as follows. So yeah, the goal of the adversary is to like produce a signature on any message of its choice. So if you like perform one iteration of this protocol in which the parties they produce a signature, the adversary now has the queries of like all but one party. And what the adversary can do is it can like basically now it can view this like distributed signature scheme as like a signature scheme that like simply performs the signing operation inside the head of a single signer. So if this is the case, then this is like basically just like another signature scheme which like has an extractor, and the extractor simply takes like all these like Oracle queries that the adversary has like detected, and it can like it like takes all these Oracle queries that the adversary has detected by like corrupting n-1 parties, and then it can like use this like polynomial time extractor in order to be able to like forge a signature for any message of its choice. So this is the idea here. So fundamentally, it comes down to this, right? If there's like one invocation of the protocol in which there are like several parties that have been corrupted by the adversary, then after this, the adversary can just like basically sign on any message of its choice, which is of course like we absolutely do not want this while like creating like a signing protocol. Okay, so of course this is for like many parties, but like if in general we only care about two parties, we still unfortunately run into like several problems if we're working in like the standard model. So schemes like Sphinx and Sphinx Plus, they usually have like an important hash query that cannot be leaked, usually a PRF key. So both of these schemes, like they make use of like pseudo-random functions, and then they have this like underlying PRF key. And if you like distribute this like signing algorithm, what happens is that like one of the parties is inevitably going to make up some kind of like hash query that it's going to like make this hash query which like hashes the PRF key. And if this PRF key is like leaked to a party which has been corrupted, then you're basically you now have problems. Because like this just like breaks the underlying security of the scheme. The adversary now just gains access to the secret key. Yeah, so this means that even for two parties now we have this problem that is if we previously we were considering like signing for like a n parties, now we're just talking about two parties. So even in the case of two parties, something like Sphinx and Sphinx Plus, you have like you cannot like efficiently distribute it in like this like black box manner. Um, yes, and let's say you want to bypass this with like preprocessing. We actually have another result based on similar lines, which shows that if you want to like sign k signatures, then you need like k steps of preprocessing. Which if you want to sign like an indefinite number of signatures, this means that like you kind of need indefinite preprocessing. So it means that like even with like some amount of preprocessing, you can only sign like a bounded number of signatures. So ultimately, I think like the important thing is like what are the takeaways we can get from this from our work? It's the following. So in general, if you want to threshold sign hash-based schemes, if you're considering these hash-based signatures from the threshold perspective, then they have that there are basically two caveats that you hit, right? The first is that either the protocol makes down black box use of the hash function. So in which case you like evaluate SHA inside MPC, or you use like some kind of like algebraic hash, which I think there's been like some new recent results on this, which support efficient MPC protocols. The downside of this obviously is that like if you want to perform like a million of these algebraic hashes, if you want to like say threshold sign Sphinx or something, then you like significantly slow down because none of these algebraic hashes are like as fast as SHA at all, and like the time difference really adds up if you're like making like a million of these. The second thing is that you can like also do some amount of pre-processing by trusted dealers. So like, if you don't have a dealer, then this causes problems from the efficiency perspective. But let's say you do have a dealer, then the amount of pre-processing is still like quite large. If I understand correctly, then the best known results, if you want to use SHA, is something like for two-party like for XMSS signing, I think it's something like 3 GB of like setup. This is as far as I know for the best known works. Okay, so we do have some numbers if you want to say that like let's see how threshold signing works if we like ignore this and like still want to do if we like still want to like proceed from a generic MPC perspective. So we signed XMSS for two parties. Like these are this is what we did. These are some of the XMSS parameters. And our like naive unoptimized implementation, this basically for computing the WOTS functionality, that's about 316.52 milliseconds. So this like adds up to like several seconds because we have to do this like several times. And for Sphinx Plus, like this is this turns out to be very bad because you have to make more than 1 million hashes if you want to evaluate them. If you like, I mean, of course, we do a very, very naive implementation. So in this case, what we do is we just like use generic MPC to sign every single one of these hashes. It turns out to be over like 20,000 seconds. So, of course, these are just like very raw numbers and they can be optimized to yield much better efficiency if you want to do like more pre-processing and like, if you like come up with like more sophisticated protocol designs because like you can like narrow down it to like a few hashes that you can do in a distributed manner and the others can be done by each of the parties. But ultimately the point is that like there is this like underlying benchmark, which is that the hash function still has to be evaluated inside an MPC for threshold signing these like hash-based signatures. Yeah, thanks. So this is the main idea.
Right. Thanks a lot for the presentation. I would just like a couple of comments. We're almost at the end, but the couple of comments are this: like the threshold signatures for is really important requirement. We don't want to lose this in the post-quantum world. We have seen that there are some naive solutions actually might be work even if they are totally naive. If in the table I showed before, for example, for Falcon, actually just combining the signatures in a naive way are better than the more convoluted solution of dilithium. And another comment I had for Mike before, he was mentioning the fact that the size of the public key matters. One good thing as well of Falcon is that you can actually paying a signature twice. So at the size, if you have like a signature 2 times, you can extract the public key, and it's actually a nice features of Falcon. But yeah, at the end of the day, we have to there trades off. Another like things that I want to highlight is like we got this 2 calls so far. That there were a lot of presentation. We set a bit of the stage, starting from 2 weeks. Hopefully, we don't have any squatter anymore. But starting in 2 weeks, we are doing some more hands-on work. So less presentation and more, let's say, we try to do more interactive calls and starting with some real work. The idea was to have like setting the stage in the first couple of calls and then going ahead. And if no one has any question, I will wrap the call today here and we'll see in 2 weeks.
Thank you.
I have a
Right.
question.
Sure.
Are we limited to the signatures we've seen here, or is there any interest in investigating the additional signatures that are being presented by NIST like Ski Sign and Feast and some of the others?
Right. No, we're not limited to this. Again, like I will say that for the next 2 weeks we'll have something concrete to discuss, and we're not limited to the signature we've seen here. What we are trying to find will be again in post-quantum. I will say there is no a single winner. There is a trade-off, and what we're trying to do probably like to analyze the trade-off and try to understand what is the best choice, but no, they're not limited on from my perspective at least. We just like the goal is to have the as green as possible on the table I've shown in the first slide today. So SkySan will be a bit. I mean, I come from the isogenies, and I'm a big fan of isogenies, but SkySan will be a bit too aggressive at the moment, if you ask me, because the assumptions of isogenies are a bit too new for my taste. But yeah, they're really interesting in terms of like key size and so on. But yeah, new stuff, and we all remember what happened 3 years ago to Psych, right? Anyway, if no further question, we're going to see in 2 weeks. And again, for the next call, expect less presentation and more hands-on stuff. All right. Thanks a lot for everyone, to everyone. And